We started this week by going over some information that can be drawn from the derivative about graphs and vice versa. So, looking at a graph, what can we say about the derivative of a function, given function f? So here, the first example gives you a graph of a function that has some jumps and discontinuities at a few points. So the first thing here we notice is that the function is discontinuous. F of x is discontinuous at x equals 2 and 4. No, 4 and 5. And in addition, we see from this that then f, where f is not differentiable, at these points either. So whenever you see you notice that there's a discontinuity in a graph, then the function will not be differentiable at the point. This is because if f prime exists at a point C, then f is continuous at the point. This is very important to remember that if a function is differentiable at a point C, then f will be continuous at that point. So if f is not continuous at the point, it means that f prime cannot be differentiable. Otherwise, it would be continuous as well. So if not continuous at the point means that the derivative doesn't exist. So here in the first example, we notice that f is not continuous here at the point 2, at the point 4, because there are jump discontinuities, and it's not continuous here either, because f goes to plus infinity as you approach 5 from the left. So certainly the function is not continuous, and it will not be differentiable, or f prime will not exist at these points either. Now for the second example, I wanted to highlight another thing. Even though this function here, well, of course, this function is not continuous at the point, so the point 4, f is not continuous at x equals 4. We see that the limit when x approaches 4 from the left and from the right is equal to minus infinity, and the same thing happens when you approach 4 from the left, and from the right you get minus infinity. So this is what we can see happens as we get closer and closer to the number 4. So certainly then we can say that f is not, it's not differentiable when x is equal to 4, meaning again that f prime doesn't exist. Prime does not exist at this point. So this is one first thing to observe. But then there's another thing, that if we look at what happens here when f is equal to 1, x is equal to 1, the function is continuous. I mean, there are no jumps in the graph of f, and the function is defined here at 1. It's defined there, and it has the same value as the limit as you approach 1 from the right or from the left. So f is continuous. However, f is not differentiable there. So the derivative doesn't exist when x is equal to 1. So remember, if we go back to the definition of the derivative, remember that we're computing the slope of secant lines, and those slopes needed to approach a limit, right? So when we approach the number c, or in this case 1, so the point 1, so when x is equal to 1, we observe something like this. So something like a sharp, sharp turn. So this means that the function will not be differentiable, because if we compute here the slope, so remember f prime would be defined as a limit. So here the slopes are negative, and if you compute the limit from the left, it will give you a negative slope. So if we compute the quotient f of x plus h minus f of x over h, we'll get some limit if we look at this expression from the left, and that will give us a negative number, and on the right hand side we'll get a positive number. Those two one-sided limits are not the same, so the limit of f of 1 plus h minus f of 1 over h does not exist when h approaches 0. Again, as I said, this is because if you compute the limit when h approaches 0 plus, you will get, I mean, you're computing the slopes on this side, which are all positive and strictly positive. And the same thing here, if we approach 1 from the left, you will get a negative number when you compute this one-sided limit. So you get a positive number, a negative number on the other, one positive number on one side, a positive number on one side, the right hand side, and a negative number on the left hand side. So the limit doesn't exist. Remember that these two one-sided limits need to agree in order to have a derivative of the point. So things that are allowed. So this is differentiable. This function is differentiable, say at this point. This point. Why, if we look at the slopes here on this side, when these slopes are approaching the slope of this line, right? And if we look on the other side, slopes are approaching the slope of the same line here. And then in this case, the function would be differentiable at the point. If you see any sharp turn like this, then function is not differentiable. So this is differentiable, and this is not differentiable. So anything like this, if you have something like that, not differentiable. The transition from one point, from one side, so from the behavior of f on one side of the point and the other side needs to be smooth, and that's the idea. And that's the idea behind the notion of differentiability. So whenever you see a graph, you know what to do now. If you see something like this, then the function is not differentiable at the point, even though it may be continuous. Okay, so this is what has to do with identifying points where f is not differentiable. Where f is differentiable. So if you look at a graph, you should be able to identify the points where f is not differentiable by noticing two things. First, the points where f is not continuous will lead to, I mean, they're the same. Well, there are points where f is not differentiable either. And the second way in which a function may fail to be differentiable is even though it may be continuous, as in this example, if there's a sharp turn around the point, then the slopes are not really approaching anything as you approach the point. I mean the limit, the slopes of the secant lines, and so the function will not be differentiable at the point. Now, an important thing. So that concludes basically what you can say about a graph. I mean, you can say something about the differentiability or not of a function. But it turns out that the graph of a function, or the derivative, can tell us a lot about the function itself. A lot more than this. So let's look at this graph. I mean, the graph at the bottom here. This is a quadratic function. This is the graph of f prime. And this is a quadratic function. We'll see that this actually corresponds to a quadratic function because it comes from the differentiating cubic polynomial. But if f prime is positive on an open interval, it means that all the slopes of the graph of the function are positive. So these are positive slopes. So whenever you have a positive slope, it means that the function is locally going upwards. So if a function is, if f prime is positive, it means that the kind of things you should expect to see are things like this. So a function that is increasing like this or like this, say. In either graph, as you move towards to the right, you move to the right to higher values of the variable x. So from point A to B, B is greater than A, then the value of f increases. So the value of f at B is going to be greater than the value of f at A. So the function is going up. The same thing here. value of the function f at b is greater than the value of the function at the point a. So the function is going up. This happens when the derivative is positive. When the derivative is negative, the graph of f should be going down. So even though a is greater than b, the value of f at a is greater than the value of f at b. Yeah, so the function is going down because the derivative is negative throughout the whole interval. So it means that all these slopes here are negative. So if you know the sign of f prime, it will tell you something about the behavior of f. For instance, in this case, knowing that f prime here is positive for values of x less than 2. So that means that at 2, for values of x below 2, the function is going up. This is exactly what we see here. So up until the value 2, the function is going up. These are the slopes. Right? So f prime is positive. And at the point 2, f prime is 0. Remember what we said about points where f prime was 0? We have a horizontal tangent line. Right, and what happens? So this is exactly what we see happening when x is equal to 2. And now what happens? The sign of f prime changes. So now between 2 and 6 is negative. So the slopes are now negative until we reach the point 6 where the slope is again 0. Remember, we know that when that happens, the function has a horizontal tangent. Okay? And then for values greater than 6, f prime is positive again, and so the function will be going up. So all the tangents here are going to be, all the slopes here are going to be positive. And we can see this behavior, that is predicted by the sign of f prime in the graph of this function, which corresponds to the graph of the function x cubed minus 12x squared plus 36x minus 16. So f prime here is actually equal then to 3x squared minus 24x plus 36. Alright, so what now? We can then ask you, for instance, given the graph below, what what among um, a few options of graphs of f corresponds to, yeah, to the actual antiderivative of f of this f prime. We're not going to give you this function here. We're going to give you a graph, say, and like this quadratic here, and then you have to deduce that among the given options, the graph that looks like this will have to correspond to f. Oh, this is the only thing that could lead to a graph like this for f prime. Okay, in fact, yeah, so you will actually have one problem where you're asked to do that in the exam. So I'm telling you right now, this example actually is taken from page 137. And basically what you need to pay attention to is that when you look, you see you're given a graph of a function like this that looks like a quadratic, then at least, at the very least, you can remember that then if f prime looks like a quadratic, then f should be like a typical cubic function. So it should look like this, or flip in the other direction. But given the sign of f prime, meaning that f is going up first, and then after a while it becomes positive again, this should be the graph of f. Okay, so if f prime looks like this, then the graph for f should look like this. This is something that we'll ask you to do or to recognize for the first midterm. And so this is something I'm telling you now. So I would go over this example given in page 137 and try to pay attention to what I've just said. I mean, rewind if you need to, and ask me, of course, if you have any questions. But this is the kind of information you can draw from the function f given the graph of the function f prime of x. Remember, the f prime is a function in its own right. Okay, so one final time, you'll be given a graph like this in the exam, graph of f prime, and you'll be asked to recognize among a given set of options what could f be, and you have to remember that the graph of this cubic is the only one that corresponds to, I mean, that is compatible with this graph of f prime. Okay, and I wanted to finish this first part by asking here in this example 4 to recognize points where f is discontinuous and points where f is not differentiable. Okay, so let's start with the points where f is discontinuous. Here we notice something funny happening at 2, so we have like an infinite type discontinuity. So 2 is a point where f is discontinuous. Nothing happens here, so you don't see any jumps in the graph of f up until 6 again. Then when x is equal to 8, you also notice something funny happens, so there was a jump, the break in the graph of f. And finally when x is equal to 10. We know already that when f is where f is discontinuous, f will not be differentiable either. So this set of points where f is not differentiable will certainly include 2, 6, 8, and 10. So what's the new thing here? Well, do you notice anything, any non-smooth transition in the function f? Everything looks fine up until 2, and from 2 until 6, oh, there's something you need to pay attention to. You see there's a corner at 4. So you see that if we look at the slopes on this side and the slopes on this side, they seem to hint that there's a problem when x is equal to 4. So that the limit that defines the derivative of the point will not exist. See, it will give you, I mean, that quotient will be going to a certain positive number if you look at the secants on the right, the negative number, and will be converging to a positive number if you look at the quotient, the secant lines approaching 4 from the left. So you see a corner or sharp turn means that the function is not differentiable either. Are there any other sharp turns here in the graph? No? Well, so that means that we only need to include the other points where f is not continuous. So 6, 8, and 10. And this concludes the analysis of this function, of this given graph. Remember, f will not, the points where f is not differentiable will include the points where f is not continuous. But you will have in addition points where you see like a corner or a sharp turn in the graph of f. In this case, there was only one point, which is x equals 4. Okay, so this is it for now. Then we'll continue with the product and quotient rule, and that will be the end of the material for the exam. The quotient and product rules are just like the name says, they are just some rules. You need to memorize them. We'll probably give them to you in the exam, so it's always much better to memorize them. They're not very complicated formulas. And yeah, so we'll just ask you to use the known derivatives, like the derivatives of power functions of exponential, in order to compute quotients and, I mean, the derivatives of products and quotients. But that's all. That's the last thing that we'll cover before the exam. That's new material. It's not really complicated, and it's just applying a given formula. Okay, so we'll see basically some examples. I mean, once we present this, the rule, we'll give just the rule, and then we'll move on to computing the derivatives using those two rules. That's what comes next.